record on this one? It's okay.
What kind of dog do you have?
Mabel, the golden retriever. Come here, dog. What's your birthday? Come here. Got the mailman out there talking to my wife. Okay, get my shoe. Come here. Look. Here. Oh, no, stay here. All right, we're gonna get tough. We're gonna get tough.
Oh,
What you think, girl? What you think? Don't like being on my lap? All right. That's funny. Yeah. Wife and the mailman are chit-chatting outside. Guess she doesn't like that. I don't know what it is with dogs and mailmen. Even friendly dogs.
it's someone trespassing on their property, I think. That's not part of their pack, so that's why I think they don't like.
Yeah. All right. So I'm going to write this down here. I hit record. I'll just put, it's 3. Maybe I better go back a minute. All right. Call that 304 here. All right. Let's see. My camera is still set up here. And then we've got, let me write this down. Chapter 21. All right. Number 43. That sounds like a good one. I don't think we've seen anything. No, we had one from, did I have 1 or 2 from chapter 21? I can't remember. All right, but I'd scroll down here. And number 43. Oh, okay. Yeah. Oh, this is a neat one here. And a pretty useful a formula at times, although I like B here because B, we tend to use B, and I think, yeah, this is trying to say A and B are the same thing. And usually B comes out to be a little easier. So keep in mind that many times we do the formula for B. Anyways, let me just talk about here. It's here, it says a cylinder contains N moles of an ideal gas, and it goes under an adiabatic process. Okay, now let me take a moment to mention this section that I did, I think both other sections today, and that is one of the challenging things about these thermodynamic problems is each processes is different because the gas is doing something different. You know, it's warming up at a constant volume versus warming up at a constant pressure. Or in this case, since they say it's adiabatic, they're saying that the gas expands in such a way that no heat energy can transfer. So that often means very quickly, or perhaps it means it's thermally insulated so that, you know, the conducting walls have a very, 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 very low conductivity here. All right. But it says, starting with the expression for work. And so we have this general formula here that says something like, and
You aren't sharing your screen.
maybe I need to, yeah, I was just, thinking myself. I said, now I'm talking here. I better also turn on my share the screen so I can start writing an equation here. Give that a second to connect. But one thing that, you know, you really want to do in these thermodynamics problems, since every process is different, is keep track of which formula applies for which case. And it gets kind of complicated, but one thing they are trying to say is the general definition of work, and I'll go back to physics 121, where it says work is just an integral of force and the direction, or the dot product of the direction it expands. That can be written in thermodynamics by replacing force with pressure and distance with volume. And since it is on the gas, there's a negative sign. although a positive sign if you use the Survey or the OpenStax convention. But this little formula, the good thing is that's true for all cases. Now you probably don't want to come back and have to do the integral for all the cases, but you can do the integral for all cases. You can do it for constant pressure, you can do it for constant volume, you can do it for constant temperature, and you can do it for no heat exchange, or what's called the adiabatic process. And that's what we're asked to do here. We're saying, look, come up with a formula during the adiabatic process. All right, so I'm going to do that. And with the adiabatic process, the pressure and the volume are related by this mathematical procedure. So again, let me keep it straight. One of the challenging things about the thermodynamics is keeping in mind what is which formula goes to which scenario. And this is the adiabatic scenario. So what I could do is replace, using this equation, the pressure. And so why don't I just, for economy of writing, call this constant K. So I could replace pressure with K over volume to a factor of gamma. And of course, the constants can be pulled out. And then the power of gamma can be written in the numerator with a power of negative gamma, because it's in the denominator and we move it upstairs. And now, of course, if you do an integral, and maybe I'll set some limits here. So we say, okay, starting with some initial volume and increasing or decreasing, but I'll just say increasing for the sake of discussion to some final volume. Then when you integrate a power function, you add 1 to the exponent and divide by that new exponent. And then, of course, you evaluate it from its limits. Okay, so I guess this would look minus K, and maybe I'll also put the minus gamma plus 1 with that. But this would be final volume negative gamma plus 1 minus initial volume minus gamma plus 1. And that's what they mean by doing this by direct integration. Actually integrate the definition of work, force times distance, but of course converting it to power and volume. Now, again, if we kind of work this out a little bit, why don't I mess with the negative sign here? I'll leave the K alone for just a second. But with that negative here, this would be gamma minus 1. This right here could be written as final volume because of the final volume to the plus 1. And then the final volume to the negative gamma can go downstairs as final volume over gamma. This one here can be written the same way. Initial volume for the power of 1 and the initial volume with the power of gamma for the negative in the exponent there. Now, if we put this K and distribute it, I'll just, instead of making a new line, do that. Watch this again, back up here with this equation that says pressure times volume to a factor of gamma equals K. Because if I rearrange it and put pressure by itself, this would be K over volume to a factor of gamma. And that's what I have here. I have K over volume to a power of gamma. I have it here. Now, of course, this is final volume and this is initial volume, but here's what that would mean. This K over volume to a gamma, final volume, would mean that that is final pressure together with the final volume. And the same logic here with that grouping. K, the constant, over the initial volume to a power of gamma would be initial pressure. I think that completes it. Yeah, so we've got 1 over gamma minus 1. We get the product of pressure and volume final minus the product of pressure and volume initial. So that is a formula that says how much work is done. And it's, of course, completely true. However, the reason I was saying is we kind of avoid that one. We need it at times. But so it's good not to forget it. It's kind of long to work out. And much, much, much easier is to think about the first law of thermodynamics. And that's what part B is here. So part B, so this was A. Part B says, hey, thinking about the first law of thermodynamics, show that the work done by a gas is equal to, and they give a different formula. Okay, now, the first law of thermodynamics is a conservation of energy one. It says if you take a system here, so here's my system, and you add energy, and you take all the energies you add. So in this case, we're going to say you could add heat energy, Q, or you can add work energy. Okay, so you can push on it. So that'd be work energy. If you put a flame underneath it, that'd be heat energy. Okay, but both of those are adding energy. You add them together, that's the total change of internal energy of your system. Okay, now here's kind of a fun little feature. Again, it's what makes the thermodynamics a little challenging because every different process is what we call path dependent. So I would say for the adiabatic, the Q being 0 means you get this relationship for the adiabatic. So instead of calculating work with a direct integral like we did in A, most of the time when we're dealing with adiabatic processes and we want to know the work, instead of going through and doing this, what we just did in step A, this integration, we take a little easier path. And so I'm going to encourage you when we're dealing with adiabatic processes, and they ask for things like work, you might want to think about what I'm about to show you here first before A, because usually this is an easier way. Because what this says is you don't actually do a direct calculation for the work. You can get to the work by calculating the change in internal energy. And what's neat about that, and maybe I should explain why, is the internal energy is the kinetic energy of those gases that make up, the kinetic energy of the molecules that make up the gas. And that is independent of how it got there. So delta E is going to have the same formula no matter whether it is a constant volume, constant pressure, adiabatic, isobaric. So here's what I'm going to do. I'm going to, even though I know I'm working with the adiabatic process, I'm going to leave the adiabatic process in my head for just a moment. And I'm going to think about the isovolumetric. because in the isovolumetric, there is no change in the volume, and therefore there's no work. So delta E becomes the same as Q, and Q we know to be NCV delta T. So not only does this give me the Q in the isovolumetric process, it tells me what the delta E is. And if the delta E is the same in all processes, then I can come back in my thinking to the adiabatic and write this as NCV delta T for the work in the adiabatic. And that's what we're asked to show. We're asked to show that the work is equal to NCV delta T during the adiabatic. So it's a little weird to look at, I think, because you're saying, okay, the work when it's adiabatic equals to this number, this molar specific heat that is used when you have constant volume, but we're not doing constant volume. And that's kind of weird. And I think it needs a little more explanation and a little more repeating to people that go ahead and know that even though I derived over here on page 2 the formula for the delta E, and it had a CV in it, of course, because I was thinking about isovolumetric. Even though I derived it for isovolumetric, I'm trying to point out it is a path independent, or a what we call a state function. And a state function means whatever equation you have, it's the same. I like to use the example of a roller coaster. We know that the kinetic energy of a roller coaster is 1/2 mv squared. It doesn't matter how it got its velocity. It could have gone from 0 to 80, or it could have gone up to 100 and slowed down to 80, or it could have, gone faster than 80, slowed down under 80, sped up more than 80, and then slowed down again. It doesn't matter how it got to 80. All you need to know is it's at 80. Those are called state functions. Those are the kind of mathematics that we like. Those are the ones where, look, you just say, oh, it has this much energy because it has this much speed. End of story. And delta E is a state function. So if you find it in one process, it would be good for every process. So feel free to use NCV delta T for the change in internal energy, not just in the isovolumetric that we derived it, but also, as I just did in part B, for the adiabatic. We could also use it in the isobarometric. We could also use it in the isothermal. We could also use it in any process that even doesn't even have a special name for it. I think I joke about the Santa Barbara process in the videos. But whatever definition, whatever process you've got happening on a PV diagram, we know that the delta E is equal to NCV delta T. Now, it's only in the adiabatic process where delta E equals W, and therefore it's the only in the adiabatic process where W, the work, equals to NCV delta T. But I'll say it again, it just, to me, looks weird using a parameter defined under constant volume and using it in a process that is not constant volume, but it does work, fortunately. Anyways, and so that was also a long way of saying 9 times out of 10, when I'm asked to calculate the amount of work done in a adiabatic process, I use this. Maybe 1 out of 10 times do I use part A. So, but both are certainly valid. Explain whether the two results are consistent with each other. Hey, this might be fun. Let's prove that they are consistent with each other. I mean, these really look like almost 2 different equations. And of course, one's based upon pressure and volume, and the other one is based upon temperature. But here's what I like to do. Keep in mind that pressure times volume equals to nRT. So if you have something like this, if you have an initial pressure, an initial volume, and an initial temperature, and then I guess I'll write it again, and maybe right below it, final pressure, final volume equals to NR final temperature. And you subtract the two. You would get final pressure times final volume minus initial pressure times initial volume would equal to NR, and then you would have final temperature minus initial temperature. So this right here was in the equation that we did for part A. So if I take my formula for part A, which says 1 over gamma minus 1, and then it says final pressure and final volume minus initial pressure and initial volume, that's this. This would be NR, and then this would be delta T. And so this is beginning to look like what we have in B. Now, there's the N and there's the delta T, but I still need that CV. Okay, but watch this. This is 1 over. Remember, gamma is CP over CV. Maybe I'll write the R here for a moment, and then the N delta T, because I'm happy with those. But down here, if I get a common denominator of CV, and then flip it, I get CV on top, and I get CP minus CV. And then don't forget that I have an R and an N delta T. Now, this is where the R comes into play. Keep in mind that we said CP is always bigger than CV by 1R. Okay, so if you ever have a problem and you want to go from one to the other, CV, the molar specific heat at constant volume, you add an R to it, you get the molar specific heat at constant pressure. So that means R is actually the difference. So this R right here could be replaced with CP minus CV, which is what's in the denominator, so they would cancel. So you would have a CV on the top left over, and then you would have your N, your delta T, and sure enough, it works out. So we can start with this formula here and put the ideal gas law together what's meant by gamma and the value of R, and of course we get the same thing. So that's kind of our proof that they are the same. This says really not prove it, but explain it, but I kind of like that as a better explanation that, hey, yeah, I mean, I can show that one equation after the ideal gas law and the definition of gamma and molar specific heat, I can put all those three things together and come up with the same equation. So the equation in A becomes the equation in B. Although again, I'd say it's probably easier to get there with the first law of thermodynamics. So that's why I say 9 out of 10 problems I like to do this. All right. Well, hopefully that was a helpful one. Let's see. Back to the chat room. All right. All right. Good, John. You are welcome. Thank you. All right. So, Anthony. Oh, I have a conceptual question. Oh, I have to go to chemistry now. So you can skip my question. I might be back later. Okay. So, Anthony's off to chemistry. Understandable. Well, kind of curious now what a conceptual question was. Because yeah, some of these are pretty tricky and they need some conceptual pieces. All right. Well, I don't see anything in the chat room. We invite you guys to jump in if you want.
Could you show that last page, Roy, quick?
Oh.
I was confused on one little one.
Yeah, the last page. I crumpled it all up. I guess so. Page 2.
Yeah. So that It's like third line from the bottom. It's the 1 over CP CV. What's the other thing?
Yeah, let me just kind of rewrite it here. So I have 1 over gamma minus 1. I'll just go up to this line. And then I have an N and an R and a delta T. So the first thing I'm going to do is this gamma, the definition of gamma is CP over CV. Okay. Then, just looking at the denominator, let me get a common denominator of CV. So this bottom becomes CP minus CV. Of course, now I have a compound fraction. With a compound fraction, we'd flip and multiply. So this would put CV in the top and CP minus CV in the bottom.
Okay, cool.
Yeah. And then the last step, which sounds like you got, was to say R is CP minus CV. So that would cancel with that. And then you just got your N CV delta T. But these thermodynamic ones can be like little puzzles. And like this problem kind of illustrates it. We really have 2 ways then of calculating the work energy in an adiabatic process. We could do this, which I'll call, we can solve it by the front door. But this is kind of a backdoor approach, where if we want to know the work, we don't really solve for the work. We solve for the internal energy. But the internal energy is equal to the work, so we get there. We just kind of came at it from the back door. It's like, wait a minute, you didn't directly do work. No. That's the front door approach. But if my job is just to get the work or to get inside, I can go front door or back door. And so you got to kind of play with these little puzzles. And so if you like puzzles and twisting them around and figuring out that, hey, this way doesn't work, but this does, or hey, I could go either way. That's the best puzzle, when you could go either way, because all you got to do is find one. Harder puzzles is when there's 2 ways, and one of the ways is blocked, and you get stuck on it. You go, I'm going to go in the front door. It's locked. So what? I'm going to go in the front door, but it's locked. All right, I'm going to try to kick it down, but it's too thick. Just go in the back door. So. Silly analogy. All right. Well, glad that helped. Anybody else out there? Ed, we haven't really had anybody from 121 today. You got anything? Yeah, in fact, I only got 1 question this week from you guys in 121, Ed, and nothing this morning, and nothing really this week. So I don't know. Is that a sign you guys are acing it, or a sign that you're so far behind you don't know what to ask?
It's kind of the situation I'm in. I'm just trying to catch up right now. So
Yeah, and it happens.
yeah, I'm hoping I can just work this weekend, catch up in physics, and then like be on track by Monday.
Monday. Good. Actually, I kind of got the same hopes. I yeah. Somehow I got overwhelmed this week, and I fell so behind on answering emails. Got like 72 in my box. I'm like, oh wait,
That's better than me. I have like 1,000 in my box.
Oh,
A lot of them are just I haven't put a filter on my
Uh,
school email yet.
uh,
So it's like just all hey, there's a sale at the bookstore, or
okay.
like all those emails.
Yeah. You know what? You should, well, everybody's got their own little skill and pattern, but to organize myself, those kind of things, like, hey, book sell, it's information that I read and then I hit the archive button.
Hmm.
And because most of those I'll never want to see again, but you're never completely sure. So then I can just go to all mail and then, go search bookstore and then it, pops up. So it's not in the trash or anything.
Hmm.
And other ones I put in a folder, like, things that are uh, related, like I might like building the summer schedule, of classes like that. Oh, this is, I'll put that over there, or hiring tutors like that. Oh, I'll put that in a folder. So I've got folders too. So if things go right, my mailbox is kind of on the low side. There are things that are what I want to be doing that day, and then jumping back to say, now put on my calendar that okay, on this day I need to go back to the folder, everything that has to do with the schedule, because if I don't get it done, say started on Tuesday, I won't get it done by Thursday when it's due to my dean, and that kind of thing.
Mhm.
But the archive is like the world's greatest button. I don't delete anything anymore. Doesn't matter what it is. I just put, maybe I have even a communication with a student. I'll go and I'll have a communication and they'll say, oh, uh, maybe they need to do a makeup test. And so we dialogue back and forth a couple times, finally set up a date. I put it on the calendar. So hopefully I set it up in Canvas, and I probably never want to see it again, but I just archive it. And then, maybe for some reason, uh, I need to see it again. I can just go to all mail and search it. Or another good one is, uh, and sometimes it just reminds me of what that student is. Maybe I had that conversation 2 semesters ago, and then something else comes up, and we start a communication, and if I just go back to my mailbox and search that name, I can go back to all the past discussions I've had with that student.
Huh. I need to start doing that.
Yeah, and it keeps the thousands of emails and keeps your mailbox more. I mean, essentially, that's what you're doing. If you're not deleting anything, you're just kind of leaving it in your mailbox as your archive. But it becomes so cluttered that you can't really use your inbox like an inbox.
Yeah, my goal over spring break was just I have my junk email, which I don't really care about. That's the email, like if someone wants your email when signing up for stuff to contact you or something, just kind of do that. Then I have my regular email, then my school email. So I need to go through my regular and my school and just sort through the stuff.
Mhm.
What classes are you teaching over summer? Or are you teaching classes over summer?
Yeah, I probably will. We do we don't do any of these major ones in the summer. It's just a little too rough to go this much material in 6 weeks.
Yeah.
But we do, and I usually do the 102 class. So I do the 102. We try to teach the 101, 102, 10, no, 110, 111.
Okay. So you don't teach 100 in summer at all?
There is no physics 100.
Was there ever?
No, our lowest is 101.
Oh, okay. That's the one I'm thinking of.
Yeah. So, yeah, and actually, we little history here. It wasn't that long ago, maybe about 5 years ago. We only taught 101 in the summer.
Hmm.
and there was only a you're welcome, John. All right. But there's only that was back in the days when we only did one summer session.
Right.
And then when they expanded to 2 summer sessions, the school was trying to go to 2 summer sessions. The idea that students would have more options, it may burn them out, but maybe they could get through programs a little shorter time frame. And that 102 was kind of a perfect fit for that, because students could take that 102. The material is not so hard that it doesn't overwhelm you in the summer, and once you got that done, then you can go into the 3 semesters: 120, 121, 122, and 123. So we were glad we did that, and it wasn't long after that before our other series of class, the 110, 111, got to be overbooked. More people wanted it than we had room in the classroom. The classroom that it sits in can only serve about 50 students. And so we were thinking about adding another section, but we really didn't think there'd be enough for a whole nother section. And then it kind of dawned on us, well, wait a minute. That one we may be able to do over the summer. So why don't we offer the whole sequence? And it had some other benefits too. The biology people, it's for the biology people, and the biology department liked that idea. They were like, yeah, because our students are working so hard in biology during the academic year, to have the summer where they can just pound out all of physics and just focus on physics and get through that would be really beneficial. So after talking with them, it was like, okay, this is perfect.
Have you ever taught the 110 and 111 class?
I did a couple years back. Yeah. See, and an interesting thing happened was I had never done the 110, 111 here. And I should emphasize here, because and it's going way, way back. I started teaching at City College in 95. So pre-95, before I was teaching full-time for a career. So it was a part-time thing. A friend of mine who I graduated with, who was teaching at Pasadena City College, wanted somebody to come in the evenings and teach that sequence, and he knew me and contacted me and kind of talked me into it. That's actually what kind of got me into teaching. I was like, nah, I don't want to go into teaching. I like what I'm doing here. And he goes, just in the nighttime, you can teach some classes. You're real good at it. And he kept hounding me, and I finally said, okay. And it was like a Thursday night. It was twice. It was a Thursday night and a Saturday morning. It was kind of a weird schedule, but I really liked it. It was really cool. And it eventually led to me to say, hey, I'm going to switch to teaching full time. But they didn't have any opening to Pasadena City College. So I looked around and found Santa Barbara and some other ones, but Santa Barbara here was the.
That's cool. Pasadena City College was actually one of the city colleges in our sport, in SBCC sports league. So the 2 years I played football at CC, we played Pasadena.
Oh, nice. Yeah. Okay. I would have thought they were a little bigger than us, or quite a bit bigger than us. But
well, so because they're a community college, they can be in our league.
Mm-hmm. Yeah, but
their campus is bigger than CC's, I think.
Okay.
I don't know. I just remember going to the locker room and.
Okay. Yeah. Yeah, so that was, I forget what I was saying about those years. Oh, you were asking me about 110, 111. So I hadn't taught it since I came up. I was recruited to Santa Barbara here to teach the majors. With my background, it was a little more hands-on and practical, and not really for life science, but for the engineering students. So that was my strength, and so I came in and started doing the 121, 122, 123 series. So I did that right away. That's all I've done since 1985, and then yeah, a couple of summers ago, we had it was the second time we'd done the series. And the one thing about doing the series is, in my mind, I think the series works best, and I think classes work best when the same teacher does the lecture in the lab. And it turned out that the teacher who normally does that couldn't do it that particular summer. So we kind of switched roles, and that was kind of a bit of a challenge. It made me have to work because I didn't have any, history on it other than going back to pre 1995. But and so the textbook was, I didn't know it real well, like this textbook. I mean, you guys can ask me stuff, and I can. Well, you saw earlier, if I want to get density, I just go, oh, density, that's in chapter 14. So I know where it is, and I can just kind of hunt for the table. But I didn't know that, so I had to stay on top of it. And it's summer, so it's fast paced. So I'd go home and kind of look at what topics they're doing. And I did remember that certain topics are a little more appropriate for the life science people. So I was like, okay, well, let me look at the book and let me kind of change a little bit from what I would have done if these were engineering students to life science students. Surface tension is an example of that one. Surface tension we don't really touch on in the fluids when the 14. You probably passed right over that when you did chapter 14 last semester or 2 semesters ago. But a lot more significant in the biology. So that and viscosities. So you can't have that little amoeba swimming without a viscosity. So you kind of skip that in engineering, but comes into bigger play when you're dealing with life science. So
I think Rylan has a question. So
okay, let's see.
It's actually just something that I'm struggling to understand. I was looking at question 54 in chapter 19, and it's just sort of about the relationship between pressure and temperature, and the premise of the question actually sort of confused me. Which is, I don't understand how it's possible to compress something and not raise its temperature. Like the air in this thing is trapped and compressed, and the premise of the question says the temperature doesn't raise.
Okay. Right.
Now, the way I think about it is like I've got a finite amount of molecules that are getting pushed closer together, so they should be bouncing off each other more, and the temperature should raise. But
now,
I'm thinking.
No. I like where you're going, and I'm actually glad you shared with your thinking, because I would say that what you just described was not an increase in temperature, but an increase in pressure. See, they hit more often. The temperature is how fast they're going.
Okay.
So the temperature, in fact, maybe you're kind of learning it in this chapter 21, 1/2 mv squared is 3 1/2 Boltzmann's constant times the temperature. So the temperature here is related to the kinetic energy of them. So if you have a bunch of molecules that are spread out, and then you squeeze them closer together, maybe a different color here, and so now they're really close together, they would hit more often. But that's a higher pressure. That is not a higher temperature. The temperature is how fast are they going. So they're still moving at the same speed, but maybe being, I'll just say, twice as close together, they're going to hit the wall twice as often. So the pressure is going to be twice as much, but their speed is still the same.
Right. Okay. I think that actually solves it for me. It's essentially the increasing the temperature, we're increasing the speed of the molecules, and increasing the pressure, we're increasing how close together they are. If you're talking about a finite amount of molecules, is that?
I would say almost, because you can increase. Yeah, I like the first thing you said, that the temperature right here, the temperature is directly related to their speed.
Mm-hmm.
Okay, and I guess maybe more appropriately, their kinetic energy. Okay.
Mm-hmm.
So assuming you're not changing the mass, we can put temperature and speed together, and that's kind of how our discussion has been going. But the other factor, pressure, let me write it as nRT over V. I would say pressure has two causes, and you only mentioned one. You said closer together, so you said smaller volume. But they could also be moving faster. So the pressure is determined by their collision, and there's two factors that go in there. One is how concentrated are they, but the other one is how fast are they going. So if I change either the volume or the temperature of a gas, I change its pressure.
Okay, gotcha.
So that's why I can squeeze this gas down, and as long as I don't hit the molecules real hard, they won't go any faster. So they will keep the same temperature, but they won't keep the same pressure because the volume went down.
Right. So
Now,
let me see, if all things are equal, then say I can change something's pressure without changing its temperature. But if everything stays equal, I can't change something's temperature without changing its pressure.
Say that last one again. If
everything in this equation stays equal,
okay,
pressure, if I change the temperature, I'm going to change the pressure, right? Like,
yeah. So if the pressure is really caused by two factors.
Yeah.
This I'd call the concentration, the number of molecules per volume, and the other one's the temperature.
Right.
Changing either one of those will change the pressure, but of course, changing neither of them would leave the pressure alone.
Gotcha.
What's really kind of weird is you could do something like this. You could, like in this picture, squeeze the gas so they're more concentrated, so this number goes up, but yet also cool it down, so this number,
and keep the pressure the same.
And keep the pressure the same.
Yeah. Okay. I think that was my thing, that I thought that, if temperature changed, then pressure changed, and if pressure changed, then temperature changed. But it's really, if temperature changes with volume staying the same, the pressure is going to change.
Mm-hmm.
And if pressure changes, that doesn't necessarily affect the temperature.
No, yeah, because there's three things going on here. There's pressure, concentration, and temperature.
Okay, cool. That helps. Thank you.
Yeah. Now, maybe not to throw an extra monkey wrench into this.
No, monkey wrench away.
But as long as you're, thinking it conceptually, because when you first brought it up, this is where I thought you were going. I thought you were going to say, if you took a piston and you slammed it down quickly, okay, not only are you increasing the concentration, but because you're hitting the molecules hard, you're making them go faster and you're increasing the temperature. So something like that, the pressure goes way up. This is the one, if you remember in the lecture video, I used to catch the little piece of paper on fire. I slammed it down really hard, really fast, because I was trying to get the temperature to go way up. And the way I do that is by hitting the molecules. So just when you move a piston down, if you move it down quickly, you maybe inadvertently make the temperature go up. So if you don't want the temperature to go up, you really got to move this piston down slowly. The pressure still goes up because you're increasing the concentration. But if you do it slow enough, you don't really hit the molecules with much impact. Or maybe even put another way, if the temperature does go up, it has time for the heat to flow out and the temperature stays the same as the bath it's kind of sitting next to or the air it's next to. So constant temperature is more of a challenge than just the adiabatic. Just the adiabatic, you just slam it down. Slam it down, the temperature goes up because you made the molecules go faster. You did work on it.
Makes sense. Cool. Thank you.
Yeah. Good. Actually, good conceptual ones because, seeing that piston go down and separating in your mind conceptually constant temperature versus, which we call isothermic, and adiabatic are different. And I think it takes a while before it sinks in to realize adiabatic does not mean constant temperature. The temperature can still go up even though you didn't add heat because you slammed it hard, you pushed on the molecule. And it sounds like you already got that. But...
Yeah. Cool.
All right, nice. Oh, Daniel threw one at me. Okay. All right, Daniel, let's look at the time here. 3:56. 3:56 and chapter 20, number 2. All right, maybe I'll tear this off. Chapter 20, number 2. Okay. And actually, this probably makes sense. It's because before the break, you were asking about one, I think close to number 1 was that Joule's old experiment. So this is his more, if I remember right, his more accurate one. Yeah.
Okay.
So if you remember the story I was telling you about Joule thinking that as his mind was developing the principle of conservation of energy, conservation of energy as well as heat is an energy. He figured that this waterfall must be warmer at the bottom, and then he was disappointed after he made his measurements. And he was thinking about it on his honeymoon, so his wife was probably disappointed too. But after he did all this stuff, and he returned back from his trip somewhere in the Alps or something. He then went into his laboratory and gave this more thought, and he actually set up one that he could measure with precision and do some numbers, and this is what he came up with. And so let's kind of repeat the same thing we did for number 1, but do it here for number 2. He said the mass of 2 blocks is 1.5 kilograms, and an insulated tank is filled with only 2 grams of water. Now, if you remember the problem 1 that we did, the problem was that there wasn't much of an increase in temperature, and part of that is because the energy was coming from the water itself. And to get a lot of mass, then that heat gets spread out and the temperature doesn't go up very much. So he realized that, so he did something more like this. He took two 1.5 kilogram masses. Let's see, apparatus. And they have a picture of it. Maybe I should go back and look at his pulley system. 20 section, oops. What's chapter 20? There we go. Yeah, so he does something like this. He puts, I thought they were counter-rotating, but his show the same thing, but all right. But the point is, there's a little paddle wheel in here. And the rope ties around. And so as these weights go down and lose their gravitational energy, they make the paddle wheel spin. The paddle wheel makes the friction or the turbulence in the water. And the idea is to transfer all the potential energy from the downward moving weight into heat energy in the water. And then he realized that if you kept the mass of the water low enough and the mass of the weight dropping high enough, there might be an increase in temperature big enough that you couldn't see in the waterfall, but you would be able to see here in the laboratory. So that's why that huge distinction. He's basically got 3 kilograms losing potential energy, giving all of that energy to only 0.2 kilograms of water. So I'm going to say the same thing here in 2 that I did in 1. It's conservation of energy, and I'm going to do this. mgh, so that's the loss of gravitational potential energy, then must go into mc delta T. That's the increase in heat energy. Now, again, what's different between number 2 here and number 1 is last time the weight going downhill was the same weight that was warming up. And so now I need to say weight 1 and weight 2, or mass 1 and mass 2. Because what's going down is 3 kilograms. Now, he doesn't have quite as high as the waterfall. What does he have here? He said, consider Joule's apparatus, the mass of 1.5 kilograms, insulated tank filled with 200 grams of water. What is the increase of temperature of the water when the blocks fall 3 meters? So he's only working in the laboratory, so he's only got about a height of 3 meters to work with. But the real important thing is right there is that the mass that he's warming up is only a small container of water. And so that's why those masses don't cross off. They're different. So 0.2 kilograms. Then we have the specific heat of water, which is what, that 4,186 joules per kilogram for each degree that warms up. So it is a conservation of energy again. And so here I have a 3 times a 9.8 times another 3. And then I divide that by 0.2. And I divide that by 4,186. Oh, and sadly, this is still about the same value. He really needs to get this, I guess what he gained in weights, he lost in height, because this was the same about increase in temperature that we got for the waterfall. So, but maybe in the lab he had a more accurate thermometer. I don't know. That'd be interesting history there. I just know that he was finally successful in the lab, and I guess we are all better off. And he didn't give up on his theory and his approach. He just realized he needed more thinking after the waterfall failure. So something to be said about perseverance.
Tell me about it. I had a question actually when I was reading this part and thinking about it, which is, okay, so you're measuring the mechanical energy out of these dropping weights, and you're measuring a change in temperature, and you record that the mechanical energy happens and the change in temperature happens. How do you know that the change in temperature is the same amount of energy as the mechanical energy when they're two different sort of, and it's all new, you know? Now we've got all these conversion factors, but how do you know that those are the same?
Well, let me, I'm trying to reconnect my phone here. Maybe I'll draw you a picture once it connects. But the short answer is you've got to design something that can transfer the energy to it. So in this case, he's thinking along these lines that if this goes down and if it picks up speed, that means the potential energy here is going to increase the kinetic energy and not into here. So he needs to make sure that his paddle wheel has enough. And that's why I thought he had counter rotating ones, because if it all goes in the same direction, it's hard to create enough friction. I thought he had something that, you know, looked like this, that one paddle wheel went one way and one went the other. He just, doing it this way, what happened is the weights just went faster, faster, faster. And as you said, the energy didn't go into the water. It just went into kinetic energy. So that is the way of telling that if you just barely let this go and it starts moving at a slow speed and it keeps moving at that slow speed, you know the energy is not going into kinetic energy here. And it's doing that because of the drag set up in this paddle wheel. And so you conclude that the energy is going into the rubbing and the friction inside the paddle wheel. And then in addition, you may even put an insulator around here saying, okay, well, if it warms up, I don't want that heat to go and warm the air on the outside. I want it to stay in the water so I can warm up, you know, I can measure the increase in the temperature.
Got it. So they did is they knew how fast the things should fall, and then they measured the difference of how fast they did fall, and they assumed that energy is the energy that went into the water.
Yeah, I think they set it up so that this big weight would actually go, you know, very slowly down. If you were kind of watching it on the screen, it would just kind of go, you know, whereas something that is, you know, gaining kinetic energy goes, and it just gains speed. And so you know you're not transferring the speed into the water. All you're doing is transferring it into kinetic energy of that falling object, which eventually is going to hit the ground and eventually make heat there. He might have even tried that at first, you know, letting it fall and measuring the rise in temperature of the lead block. But again, if you do that, this is, I understand, if I understand his history right, that you know, if you just let a weight fall, then these two became the same number and they cancel off, and you don't have the advantage of making a heavy weight go down and warming up a lighter weight. So that was really a big insight to him, was to say, okay, what we're going to do is we are going to let a big weight go down and only warm up a small amount of water.
Cool. Thank you.
And he was locked into using water here because he was trying to see how many joules were equal to a calorie, because the definition of a calorie existed before people knew, or scientists knew, that heat was an energy. They just defined a calorie as the amount of heat needed to raise 1 gram of water 1 degree. And it was Joule who started going, you know, I think heat is an energy and therefore shouldn't be measured in calorie, but should be measured in, and at those times they didn't call them joules. They just called them a kilogram meters squared per second squared. You don't get the honor of having the units named after you till you die. So, yeah, you don't call them a joule until after it's post-mortem honors. So it's kind of the opposite of the Nobel Prize, where you can't get a Nobel Prize if you're dead. There's no post-mortem Nobel Prize, which is, good or bad.
Yeah, who knows?
Well, that was when Nobel set up the prize money. He wanted it as a seed to feed more development. So he wanted it to go to the best developments of the year, and then to that person so they can do more. And so he made it very clear, no post-mortem Nobel Prizes. It's not, today we kind of think of the Nobel Prize as an honor for the best scientific work, but that is not the way his will, estate, whatever it's called, set it up. He set it up as a prize money so that science could advance.
Yeah, it would sort of take the pressure off of someone to need to get grants or support themselves, so they could, if they were truly this genius, they could just think about the things they wanted to think about and not have to worry about money.
Yeah, exactly. That was his thinking. So I kind of think, I wonder if we need some kind of Nether Prize for great scientific discoveries.
They have the MacArthur Genius Grant, which is a similar thing to that. It's again given to living people, and it's not just in science. It's like across disciplines, but they'll sort of pick someone who's doing, they think, really meaningful work in their field. And I think it's less than the Nobel Prize. It's like a couple $100,000. But the whole idea of it is to allow them to do whatever they want to do for a little while and not have to think about money.
Yeah. So yeah, I get it, but I think people like Hawking's then will probably never get a Nobel Prize. It kind of hurts the theorists because they come up with good ideas, but a lot of them aren't really verified and tested and proven until long after they're.
Yeah, that's a good point. It's like they have these great ideas, but then the actual physical testing isn't there.
Right. So if that takes decades to develop the testing, they could have passed, and then great discovery, but because I think Hawking's radiation will eventually prove the test of time, and but I think he'll have passed and won't get his Nobel Prize for it.
Are we talking about Stephen Hawking?
Yeah. Or did he pass? Oh,
he did pass. Yeah.
Yeah. Okay. Yeah.
He died literally, I think it was a couple days before the first picture of a black hole was taken.
I remember that year. Okay. Yeah, that's like 2 years ago or 3 years ago.
Yeah. So I'm pretty sure he died like right before he could see all his research done, which sucks, but I mean, happens, I guess.
Hopefully they name a unit after him.
Yeah, there you go.
I had another problem.
Go ahead.
It's number 52 from chapter 19. I'm getting caught up on my problem sets right now. I've been working through it.
Don't worry, I'm doing the same, Rylan.
Okay, cool. I feel a little behind, but it is what it is. Yeah,
it happened. Although I just probably should give you a little warning here then too. We've got it's hard to believe, but this weekend we'll be turning the corner and going into our fourth and last chapter on thermodynamics.
Yeah, no, I know. I'm trying to spend pretty much all this weekend doing physics to get caught up, so that next week I'm there. I mean, I've got everything read and I've got all the videos watched, but I've just got a lot of problems to get.
Yeah.
Um,
Well, it sounds like you've got a good catch-up plan, so
Yeah.
that's good, because
I'm pretty much done with chapter 19's problems, and so I just
that would make the test, what, 11 days away? So
oh boy. Okay.
put it in perspective. So yeah, stay on pace.
Yeah, no, that little kick of panic is just what I need.
Yeah, it's at 11 days, it's not enough to make you overstressed, but it is hopefully enough to put a fire under you.
Yeah, I've learned in this stuff. I'm trying to learn this stuff that like 11 days isn't that long. You know, when I really think about how long it takes me to truly like get good at the stuff,
Yeah.
it's like 11 days goes by in the blink of an eye. So
Yeah.
anyway.
Well, good. And you've learned something important that some people mistake in physics 121. Usually they learn their lesson, but this stuff just takes a while to sink in. So you can't say, well, it's going to take me, 30 hours to learn it. You can't just commit 3 days before the test and do all 30 hours. You can't go, I'll go 10 hours a day for 3 days and I'll learn it. It's 30 hours, but it needs digestion time in between.
I have this thing. I don't know if this ever happens to you, Danny, but where like I will I'll be working on a problem late at night and I can't figure it out, and I'll go and just sleep on it and wake up and be like, oh, I get it now.
Good.
Yeah, that's happened to me several times where it's like I think it was math 200 over the summer. I couldn't figure out the problem, and I'm like, you know what, it's the last problem. And it was like the night it was due, so I'm like, I'll just turn it in first thing in the morning. So I went slept on it, and then woke up, and I'm like, oh, I know how to do this problem, and was able to like finish homework. So it does happen.
Yeah, sometimes I swear I'll wake up and it's like it's on the front of my brain. It's just like, oh no, you're thinking about that wrong. It's like you do it like that. It's fun.
It's amazing how the mind works sometimes.
Yeah, totally.
Yeah, good. Yeah, that happened to me a lot too. So got my my lighting seems different today. I haven't really looked at my own picture, but I'm all blacked out.
I was thinking this. Well, I think everyone's lighting is kind of different because normally I don't have that glare from the outside window.
Oh yeah, yeah.
For some reason, it's just like super. It's like has a lot of extra glare today. Don't know why.
You can point the light in my face, but that's kind of painful. I don't want to do that.
Yeah.
All right. Well, I'll just kind of be silhouetted back here. Nobody wants to look at a bald old man anyway. Fat bald old man.
No. False.
Okay, so let's work on this one. Oh, good. It says review problem. So this is going to do a little throwback to 121, huh?
Yeah.
All right. So it says, following a collision in outer space, a copper disk at 850 degrees Celsius is rotating about its axis with an angular speed of 25 radians per second. As the disk radiates infrared light, its temperature falls to 20 degrees Celsius. No external torques act upon the disk. Now, I think the review part of this is conservation of angular momentum. So we know that the initial angular momentum equals final angular momentum under cases where the net torque is equal to 0. And so this would be what I call a rotational problem. I think this would be right out of chapter 10, I believe. Following from chapter 9, and just as a review, we know that initial linear momentum is equal to final momentum so long as the net force is equal to 0. So I think that's why they have this thing just kind of spinning in outer space. Nothing's touching it. There are no torques. So we know that the angular momentum before and after is 0. So I'm going to put here I initial omega initial must equal to I final over, times omega. No external torque. A, does the angular speed change as the disk cool? All right. Explain how it changes and why it does, and what is the angular speed at this lower temperature. So taking this, and maybe I'll just put a little circle around this equation. This would say if you have some initial conditions here, if one of these changes, and in this case, moment of inertia is related to the size of the object, which this chapter 19 is about thermal expansion, or at least one thing is about a thermal expansion. So they're trying to say this is going to change. And of course, if that changes, then the angular speed changes. So yes, the angular speed changes. In fact, hopefully this kind of sounds like a problems that you would have done in 121, where you had somebody spinning with their arms out. Usually kind of the analogy is an ice skater. And as the ice skater spins around, their arms are out and they pull them in, and that makes them go faster and really get spinning really, really quick. Another good example is like a gymnast, where the gymnast will jump off the floor. As they jump off the floor, they tuck in, they make themselves into a tight ball. And again, they're trying to lower their moment of inertia. And as the moment of inertia goes down, their rotational speed would go up, because you got to keep the angular momentum the same. All right. So that's really what this problem is, and that's why it's a review problem. Now, they say it's a disk, so we need to know something about the moment of inertia of a disk, I think. So if I turn back to chapter 10, I would see that 1/2 mr squared. And so let me put initial r would be then the moment of inertia of this disk. What is the angular speed? Okay. Now, I was thinking they might have given me some information, but it looks like they're going to make it a little harder. I don't have the M and the R. And I was about to write an equal sign, but I see that it locked up. Oh, and paused for some reason. Let me redo. Okay. While it's catching up, I'll just say it again. I was about to put an equal sign there, and I think I still will. Okay, so I'll put an equal sign. Okay, so this is the moment of inertia initial. This is the angular speed initial. Now, the final would look something like this. It would have an 1/2, it would have an M, and the new length would be this. It would be the original radius, or whatever that is. And then it would be plus alpha R initial delta T. Of course, it would be now squared, and then omega final. So it looks like I'm going to have to be a little creative with the math here, because they didn't give me the mass or the initial radius. Fortunately, I don't really need it. If you look here, the initial R is in each of these two terms and can be pulled out and then squared. So then I would just be left with a 1 plus alpha delta T squared. And I got to admit, a moment ago
That was
when I
a
was
mathematical step I was uncomfortable with, which was just pulling something out of something that's squared.
Okay, maybe I should.
No, I mean, if that's a legal move to do, I'm happy to do it. I just, for some reason, had always thought if I had something squared, I needed to square it all out and deal with it.
Okay, and okay, and so let me show you. I did a couple of steps here. I did this. So what I actually did first was factor out an R from each term on its own. I think you're good with that, right? Then I used the exponent and distribute it to each of them.
Yeah, that makes perfect sense.
Yeah, it's kind of two steps that, and because it's two steps, you may not recognize it. It kind of depends, on if you've done it before and how much math, you feel comfortable.
I like it, but for some reason, I just had always never thought. I'd always thought that the square meant I couldn't do that, but it makes perfect sense.
No, but I like the way you're thinking. That's a good way of thinking because it really is justified with two steps. And then once you get, once you've seen it now, you'll probably never do both steps. You'll go, oh yeah, I can do that. I've done it before. Yeah. Okay, so now that I justified it for you, let me just kind of cross it off my screen here. But see, this is the part that was kind of bothering me as I was reading this, going, oh, what are we going to do? Because we don't know the mass, but see, they cancel off, and we don't even know the initial radius, but it too cancels off. And that's good. Because then I just have 1 plus alpha delta T squared. And I think in this step here, I do know everything except for final speed, so I can get it. I know how much it changed. I can look up the coefficient of, let's see, was this copper? Collision in outer space. Yeah, copper it is. So I'm going to look that up, and I'm given that initial speed. So let me put in those numbers. So this is 1/2. The initial speed was 25 radians per second. This is 1 plus. Now let me jump over to the textbook and going to chapter 19. Here we go. Here is the chart. What is the measured thermal expansions of copper? Looks like copper is a 17 times 10 to the negative 6. And of course, the temperature drop is a negative. Final minus initial is a cooling down. And so I'm going to grab my calculator because it cooled down quite a bit. So final is 20. Initial is 850. I guess I don't need a calculator for that. But it's a negative 830 degrees. And of course, I'm kind of glad they gave a big temperature change because, this is so small that it's tiny, tiny, tiny. But you can also see the negative temperature change means it got smaller. And as we talked about at the beginning, smaller moments of inertia would mean faster angular speed in order to keep the angular momentum the same. So I expect something a little bit more than the 25. And so now I can grab my calculator here. Now that I have the negative 830, I'll go times 17 times 10 to the negative 6. That's that number. I'll add 1 to it. I'll square it. So that's this side of the equation. Over here, I'll take a 1/2 and multiply it by 25, and then I will divide by that number I had on the other side. And it looks like I will get, oh, well, that was dumb of me. I guess when I got lost here, I apologize. There's, besides canceling off the M and the R, I should have also canceled off the 1/2. And for some reason, I dropped it right here. That should have been canceled off. Okay, so there shouldn't have been a 1/2 there. I'm going to try that again. So 25 divided by, and it would have been this number up there. And so a little more than 25. So final speed would be 25.7 radians per second. Good.
Cool. Yeah, that's, I think it was in the solution, I was not thinking clearly about the math because it was really just that little mathematical step that I, for some reason, wasn't following. Yeah, but that makes sense.
Thank you, Dr. Young. I'm gonna go take a break and then get back on physics later in a little bit.
Yeah. Okay. Wow.
Yeah.
Wow, the day went fast. Yeah, we're already at the end. Good deal.
Yeah. Have a good weekend. Bye.
All right. All right. Work hard. 11 days. Count them down.
How you doing, Michael?
Hey, TJ. How you doing?
It's been going. I've been doing pretty well. How about you?
Good. I'm doing well.
Nice. Yeah. No. Last week was. I really liked the applications of physics or of Newton's laws but I liked the section. But yeah, like it's the quizzes are so hard, man. Like I don't know how anybody does them because I get so stressed out doing them. But yeah.
Okay.
How do I get better at doing the physics problems like fast? Because I understand how to do them, but even with like 30 minutes and then with like I can't. I don't have any really time to slow down and think about it like so much, or maybe I don't know. You know what I mean?
Well, I do, but there's also. Well, there's a couple of answers depending on what you struggle with, but the part I'm trying to say here is Newton's laws. I like to say there's a 4-step process. I don't know if you saw any of my videos.
Yeah, I did. I watched your lectures. Yeah.
And those 4 steps you can use every single time. So they if you commit them to memory, but then it takes practice and say, okay, how do I do this? And then I do the next step and do the next step. That's how you build up the speed. And so you begin to see that the physics is universal and it applies to every scenario. Now you have to then to pick up speed, see how I can quickly apply this universal principle to this scenario. That's tough. And that comes with experience. For some people, you could do that in a couple of homework problems. I got to admit, I always assigned quite a few more homework problems than what you guys are assigned. And so I would encourage, and maybe that's good for some people because they can learn it in those few steps, but for some people,
I did those homework problems over and over. Like I probably did the homework 3 times over, and then I got used to doing it with like solving for those variables. And then on the quiz, the variables changed up and it threw me off. Yeah.
Oh, yeah. And that's what I was about to say, that going over the homework problem is okay, but I don't think I would go over it more than twice.
Yeah.
You know,
For
once
sure.
you go over it twice, here's what you miss out, because the concept of universal law of gravity is, I mean, Newton's three laws of motion is that they're universal.
Hmm.
And if you keep looking at the same problems over and over, you think you really understand them. What you really need to do, though, is see them from a different angle. There's
Yeah.
just so many different approaches they could be applied. And you almost give yourself a false sense of knowledge, security. You think, oh, I'm doing them fast now, but you're really knowing where to go already. And the hard part is taking a universal principle and applying it to that particular problem. So I think you should do all the homework. You should even do it twice. But after that, you should do other problems in the book, either
Yeah.
the Stacks book or the Survey book.
Did you end up sharing your old 121 homework? I can't I actually don't know if I got that or not.
You know, I don't remember. I remember writing a note and saying I was going to do it, and then I sent something out, but
Maybe
that might have been another solution. Let's see.
I can check my email. Let's see.
Yeah, I will check what I sent out. Although now that I'm thinking more deeply about it, I'm thinking, yeah, maybe I did.
Let's see. Some examples.
Because I thought I said something like old homeworks, and here's the video links. And then there's even the solution page. I want to say yes.
Okay, here, wait, maybe this. No, this video. Let's see. Yeah, I've been trying to do extra problems just from off the internet. I probably should be doing. I don't know why I do them in the book, but I find that lately I've been all I've been doing is school, and I've just been kind of going a little crazy. Yeah, I'm taking like 4 or two CS classes and then physics and then multivariable calc, which I all really like, that's the good thing. Let's see.
Yeah, good.
I can't seem to find the problems.
Yeah, I don't think I did. I can't find it yet either. I'm trying to think of what I would have called it. Oh, I know, but I would have sent it to your class, 617. Here we go. So let's see, video solution to ramp. Okay, that's the recent one. Video.
I'm excited for this next chapter. I've been starting to read the book and then the lecture notes or whatever. And it's really interesting to me, the kinetic or because of I work with some of this stuff. Let's see.
No, I don't think I did. It looks like I sent this, and maybe I thought I was getting it all covered. I sent when was this? February 9th. It looks like I sent my video lectures, but not the homework problems or the solutions. And this goes all the way back to projectile motion stuff. Nope, I did not. All right, I will send those out.
Awesome.
Yeah.
Let's see.
Oh, I see. You know what maybe this confused me. It looks like an individual student asked, like Mo asked, and I sent her stuff. And I just never but I didn't send it to a group. Yeah. All right. Well, I'll need to do that after I. Well, I'll take a little bit of break here in a second, and then I'll come back here and do all my Zoom videos and send those out, and I'll send this out too, and maybe even some stuff. You guys are doing energy right now.
Yeah, right now we're doing energy. Yeah.
Okay.
Let's see, I can. One sec. Let me pull up my page.
Oh no, wait, is it? Well, today's the end. Don't you do like a quiz today on?
Yeah, the quiz. I did the quiz yesterday, but
Okay.
yeah, the quiz closes today. So
Okay.
let's see. Yeah, work, power, and kinetic energy, and then work by gravity and springs. So that's like, is that Hooke's law? Let's see. Then work done by friction too.
Good.
Yeah.
Yeah. And actually, I think that's a little bit of breathing room too. I think I think they're good problems. I think you'll like them, and they're usually easier than Newton's laws.
Yeah, Newton's laws were definitely a challenge. I didn't think, or I didn't realize how challenging they would be, especially once you add the friction force. They can be a little challenging. But yeah, let's see. But yeah, so you would just suggest to get faster at doing them. I mean, obviously practice, but yeah, is there any other